These maths teachers are taking part in a project that's looking at the ways ICT can help with hard-to-teach secondary maths topics. Leading the project is Alison Clark-Wilson of the Mathematics Association and her colleague, Professor Adrian Oldknow.
Everything else changes on the screen.
The group has come together to share resources they've developed and used with their own pupils. What each topic has in common is the use of ICT to tackle a traditionally tricky topic.
I've been looking for some time at circle theorems and using ICT to support that.
Ruth's circle theorem project uses dynamic geometry software, which allows pupils to make and manipulate their own geometrical constructions.
This is the one we liked, didn't we? You know, they've done quite a lot there, and I'm particularly interested with these students to look at geometrical reasoning and also proof.
Ruth hands out the prompt sheets and cards for her Year 9 pupils to get started.
From the File menu, choose New Sketch. Construct a circle. From the Construct menu, choose Line.
They've used this software a few times before and have done some work on the properties of triangles.
Now you've got to construct an isosceles triangle with the odd angle at the centre.
The odd angle of the centre?
Yeah, you know how to do that.
Right.
Click that one. Where did you start?
The students have set up the software to display the angles in their triangles on the screen, and it's not long before they come up with some conjectures.
Every time we move the C angle, the other angles all change.
When you move the points around the circumference, all the angles change in the triangle when it's in a circle. Apart from...
What's the one that stays the same?
That one.
Only two change at a time. So you can write that down.
It was asking about, like, if you made a triangle, what the angles would be if you moved points around the circumference. As we did there, we found out that B would always stay the same and A and C always change. But A and C, when you add them up, they'd add up to 90 degrees. And B would always be...
Pupils working on the orange cards begin to devise some actual proofs.
Yeah, we cut it in half, so there's two isosceles triangles.
Ah, right, interesting.
Because we've been learning about isosceles triangles.
So isosceles triangles are pretty important.
Yeah.
Ah.
And the measure angle.
I know you want to measure some angles. Okay, I'm going to leave you to that one. I'm going to come back to you and see how you get on.
Measure. 46.
Should that be equal to that?
Yeah.
We'll just make sure.
I'll cut it into two to make two isosceles triangles on both sides.
Good.
And that means that the two opposite angles should be the same size.
Good.
And there should be one odd angle.
Good.
So I worked out the middle angle.
Yes.
And from that I got the other two angles. So
Right.
I divided that by 2 to get the other two angles.
Right.
The angle, it make some points going to the middle from angle A and C.
And to measure.
And to measure them.
And then it's so just what do we notice? And we notice when we move like the angle B, it's at 70, say here, it's at 72.85 degrees.
How would they have tackled this project without the geometry software?
Normally, you can't really move angles on a piece of paper, really. It won't really do much, will it?
It's basically impossible.
So, a computer using this software is really good because it lets us experiment. While it's not that hard, but you can learn so much.
I decided to go away and look at one of the things I thought was hardest to teach, which was...
Before she used the materials with her pupils for the first time, Aisling showed Professor Oldknow what she was planning to do. He's an acknowledged expert in how to use this software.
One of the most important features of Cabri is the fact that we can actually open up a shape.
Is that something they've tried before, or will it be something quite new when you do that?
Some of the students should have done this before when studying nets.
Right, OK.
So we're looking at the fact that this is a right-angled triangle.
What is so hard for pupils about working in 3 dimensions?
The hard-to-teach element is the fact that we're no longer dealing with a rectangle.
It's so hard to teach, it's usually not done. It's usually cut out. I mean, the amount of 3D...
It's having a bet with his friend Jasmine. And the bet is about...
Put a line through it. Work out the length of this one, then we know, like, how how long the stick can go in there.
We can use Pythagoras.
Measuring it that way is going to have a longer stick than measuring forward like that. So we're going to measure it that way to see how long the stick can be.
They then look at an interactive version of the same box made on the software.
Thank you very much, Vivian. OK, so Vivian has actually opened up the box so that we can see inside of it. This line, which is one of the sides of our cuboid, is 8.2. The length of that segment, 11.5. Well done. I'm going to rotate the shape so we can have a look at it from different angles.
Is it triangle?
Does anybody have anything they want to mention? Denai?
Yeah, you can see a triangle inside of it. I think it's from points E, G and C there.
So you want me to go from point E to G to C. OK, let's rotate that and have a look at it. So if we don't know this length here, how can we work out?
Mathematically, Aisling believes it's important for pupils to back up what the software can do with the written methods they're expected to use in the exam.
We're trying to work out the pink triangle at the top first. Find the hypotenuse. So it's 5.5 and 8.2.
Yeah, 5.5, 8.2, and the hypotenuse
equals c squared. 8.2 squared is 67.42.
The next task asks pupils to use the 3D software to work out the angle between the diagonal of the cuboid and its base.
So you're using open polyhedron, and now you can pull down the next one. So what should you do first, do you think?
find a segment. Do a segment.
Super. So go to the segment tool for me. From A, yeah, to super.
T provides a stimulus for mathematical discussions.
So first to find the length from A, B and C. That's going to be a triangle. That's a right angle triangle right there.
So now we've got all our lengths in our triangle. How will we work out the angle?
I think you should just go on the angle one and then just measure the angle.
Okay, super. Off you go. How would you check that this was the right angle?
Do like
another line there.
Yeah. Segment.
Some pupils move on to work out the longest pencil that would fit into a square-based pyramid.
Oh, first we have to open it. I like this one. I like it.
Do you think that's going to be longer than maybe something coming down from the top?
We predicted that the longest side is going to be from there, from one corner to the middle of the pyramid, which came up to 7.6. Now, what we need to do is just find the angle of it. So we're going to work it out using Pythagoras' theorem. And see right here.
The larger the volume of the cuboid, the larger the angle between the diagonal and the base.
So there's your volume. What else do you need?
And then extend.
You can actually make it empty. So now you can see through the shape and you can see your diagonal clearly here.
And I was thinking really about algebra and sequences and thinking about how I can link together the many representations of sequences.
Jay's project involves using this handheld computer device to investigate quadratic functions and number sequences.
This function is x squared.
Jay then downloads the files the pupils will need from his laptop onto each of their handheld devices.
The number
software.
How many squares were there in the first one? Yes, Connor.
1.
In the second one, there were
4.
4. Thank you very much.
9.
There were 9. Very good, very good. And in the fourth one, there were, going over to Matthew...
16.
16, thank you very much. So, that one represents 1, that represents 4, that represents 9, that represents 16. I'd like you to type them into yours as well and make sure that they're appearing on yours. That's fantastic. And you can put the fifth one in as well if you want to.
Jay's Year 8 pupils have used these handheld devices before to look at straight line graphs, but this is the first time they've encountered quadratic functions. Now, they're trying to find the graph of an equation that fits the points they've plotted.
You could put a square key and then you could put a number in there. 1, enter.
I pressed X, then I pressed the X squared button, then I pressed enter, and it just curved.
Now let's think about this for a minute. If those are your X numbers, X squared becomes your Y numbers, and then you get a graph like that. Okay. Equation. So how could we get the equation of 1?
0.
You're right about
3,
that. Good points. Maybe later on.
15.
Sorry?
X squared, and we press enter. It's a bit off. So then we thought, what could we do?
But then we realised that every single number down here is 1 less than the squared number in the last one. So we thought if we put -1 at the end, it might give us the answer.
-1 here.
Sure.
And then press enter. It's on the line. And we got
that didn't try it.
No.
This could be right.
Then 1.
Okay, now, what? 1. Oh, look, and you can just see that is 1, because there's 0, there's 5, and that's 1. Okay, I think you've worked really well today, so we'll stop there. Thank you very much.
So what was Jay's reaction to the lesson and his pupils' work?
So much happened, really. What struck me as significant is that